So we're going to be looking at a proof of the geometric series formula. So a geometric series is a sum of the form a times r to the k for some constants a and r. Let's start by looking at the expansion for this. So we would start with a times r to the power of 0, which is just 1 times a, plus a times r to the power of 1, plus ar squared, ar cubed, so forth, until we get to some ar to the n plus ar to n plus 1, and it continues on to infinity. Let's look at just the partial sum, the sum of the first n terms. We could write that as the sum from k equals 0 up to n of ar to the k. So let's multiply this partial sum by 1 minus r and distribute this term to the 1 and the r. So we'll get the sum of k equals 0 up to n of ar to the k minus r times the sum of k equals 0 up to n of ar to the k. Now we can bring this r into our summation for this term. So this term stays the same. And here we get the sum of k equals 0 up to n of ar to the k plus 1, which comes from r to the k times r. Now if we think of the expansion of these terms, for this first part we get a times r to the power of 0 plus a times r plus ar squared plus plus a times r to the n. Remember, this is a partial sum, so it's stopping at n. Now if we look at the second part here, we're still starting at k equals 0. If we plug in 0, we get a times r to the power of 0 plus 1, which is just a times r to the first power. If k equals 1, we get a times r to the power of 1 plus 1, which is ar squared. And if we continue, we'll eventually get plus a times r to the power of n. Our last term would be when k equals n, which would give us a times r to the power of n plus 1. And remember, we're subtracting this, so I'm going to put this in parentheses with a subtraction sign here. So now if we subtract these two terms, you'll see why I've lined it up in this way, because we get a telescoping sum. So this a times r cancels out with this minus ar squared and a minus ar squared cancel out, and all the middle terms cancel out, including a times r to the power of n minus a times r to the power of n. So all we're left with is this first term and this last term, which is just a times r to the power of 0, which is just a times 1, minus a r to the power of n plus 1. Remember, here our equation started with 1 minus r times the partial sum, so I'm going to bring that down here. Our goal is to get to the sum of the infinite series, so let's take the limit on both sides as n goes to infinity. On the left side here, this 1 minus r has nothing to do with n, so we can think of bringing that outside the limit. Taking the limit as n goes to infinity of this partial sum, we just get this 1 minus r times the sum from k equals 0 up to infinity of ar to the k. On the right side here, this a, the limit as n goes to infinity of just a, we're just left with a, and the limit as n goes to infinity of ar to the n, or r to the n plus 1. What if we consider absolute value of r being less than 1? Then this limit is just 0. So this term goes away, and we're left with just a on the right-hand side. Now we're almost there. We can just divide both sides of the equation by 1 minus r, canceling it out on the left side. And we're left with the sum of k equals 0 up to infinity of ar to the k, which equals a over 1 minus r. And this is our geometric series formula.